Yeah. Okay, good. So hey everyone, and thanks for coming. So today I'm super excited to introduce Tristan. So Tristan has been doing his PhD in Yoshua Benju's group, and he has been working on causal discovery using generative flow networks. As you've heard, he's soon going to defend his PhD. And I think he's done a brilliant PhD, so I'm very excited to hear about some of the things that he's been doing. And Tristan, take it away.
Thanks, Lance, for the kind words, and thank you, everyone. And thanks for inviting me to talk in this group. I think it's very relevant to things that we are all interested in, and I'm looking forward to the discussion afterwards. So today I'm going to talk about causal discovery with generative flow networks. So generative flow networks, you might have heard Joshua Benjo talk about it recently. These are also called GFlowNets. So today I'm going to talk about causal discovery from a Bayesian perspective. I'll introduce that. Then I'm going to go do a very brief overview of what GFlowNets are. And then finally, how we can use these models, GFlowNets, to do causal discovery from a Bayesian perspective. So just so that we are all on the same page, but I'm sure a lot of you know about these things. Today we're going to talk about causal Bayesian networks. So this is going to be the framework of choice to represent causal models. So there's a lot of different models that we can use, but today I'm going to focus essentially on the causal extension of Bayesian networks. And so Bayesian networks by themselves, they represent a distribution over multiple objects, over multiple quantities, sorry, as a directed acyclic graph, as a DAG. So we have an example of that on the right-hand side, where we have 4 different random variables, which are all connected to one another. And so the very specific thing about Bayesian networks, just the regular Bayesian networks, is that it's going to provide a factorization of the joint distribution between all of the quantities in the system of interest. And this decomposition depends on the structure, on the DAG structure that we specified. And so the way that this is done is that we're taking the joint, and this is a product of the conditionals. Each conditional can be read from the DAG itself. So usually the structure of the DAG, this is something that is given by some expert knowledge that some experts know something about the system that we want to model. And so they are encoding all of the assumptions about the system inside the structure of the Bayesian network. And so this is usually what we do. We have the structure of the Bayesian network, and then we can do a lot of things with that. So we can train the parameters of these Bayesian networks of the different conditional distributions, but we can also use that as a tool to answer either probabilistic if we're just in a regular Bayesian networks, or even causal queries if we're talking about the causal extension. So one query that we might want to answer might be, what is the effect of a particular feature in the X-ray on the final diagnosis that we are making about a patient for a certain disease. So this is all based on the assumption that we know what's the structure of the DAG for the Bayesian network. But now the question is, what happens if we don't know the structure? And so this becomes a new challenge, which is called structure learning. So structure learning is really about when we don't know the structure of the Bayesian network and we want to learn it from data. So this is kind of an inverse problem where we have data and we want to learn what's the structure of the Bayesian network. And a lot of times, what people have done in the past is to learn a single best DAG as by maximizing some score. So this is what we call a score-based method, where we define a score that can give us a sense of how well the graph, some specific DAG, is going to fit the data. And then the goal is just to maximize this score. So a very simple optimization problem at first glance. But the big challenge is that, so there are two main challenges that I want to highlight. The first one is that the space of graphs is something which is discrete. So even though this optimization problem seems fairly easy, and even if the score was somehow differentiable in some sense, we wouldn't be able to use some of our favorite tools from continuous optimization, gradient descent methods, and things like that, because the space itself is a space of discrete quantities. So we won't be able to do something like that. But the second main challenge is the number of DAGs, so the space over which we want to search this single best DAG that is maximizing this score. This is something that scales super exponentially with the number of nodes. And so to give you a sense of how fast these things grow, there are about 10 to the power 18 DAGs that you can create over 10 nodes, so a very small system, and already we have a very large space. And then if we move to 20 nodes, we have 10 to the power 72 DAGs that we can create over that. And so this means that we need to find, if we have a system over 20 quantities, we need to find the best single DAG over 10 to the power 72 candidates. And this is something which is absolutely immense. We cannot do this kind of optimization in a reasonable amount of time. So that's the main challenge of structured learning. But there are some other limitations of structured learning just inherent to the fact that we're looking at Bayesian networks. So the first one is that when the data set is small, and we want to find that one single DAG that is maximizing this score, then we might make some little mistake, because if some mistake over which DAG is going to have the best score, because maybe we have multiple DAGs that are explaining almost equally well the data that we're seeing, and we have a small amount of data, but then we're just going to take almost an arbitrary decision if we just want to maximize what the score is, and we don't take into account the fact that actually there are multiple possible DAGs that could explain almost equally well the small amount of data that we have. And so when the data set is small, something that we might want to take into account is this epistemic uncertainty that we have over the graph structures. And then there's a second problem, which is more specific also to Bayesian network, which is this notion of Markov equivalence. Because what I said before is that when the data set is small, maybe there are multiple DAGs that are almost equally explaining the data. But what we have with Markov equivalence is that even if we had an infinite amount of data, there might be multiple graphs that are going to encode the exact same assumptions about the system. And when we say assumption here, it means just conditional independencies, or when it comes to causal Bayesian network, it might be something a little bit finer than that, but there might be multiple graphs that are encoding the same assumptions. And so from the point of view of data, from the point of view of observations, if we have two graphs that are Markov equivalent, they are going to fit the data equally well. And so the classical example that people use when we're just talking about Bayesian network is this system where we have just two variables. So just to give you a concrete example, let's say we have one variable, which is the reading on a barometer, and then another random variable, which is the actual the weather that we're observing outside. And so if we're looking just from observations of both readings of the barometer and what's the weather outside, what we'll see if we gather a lot of data, we'll never be able to distinguish between these two DAGs that would equally explain the observation that we're seeing. It could be either that the reading of the barometer is causing, quote unquote, what's the weather that we're observing outside, or the other way around. And so we know from intuition that it's actually the second one that is actually happening in the real world. But if we're just based on data, and even if we have an infinite amount of data, this is a distinction that we won't be able to make. And so all of that to say that if we're choosing just a single best DAG to explain the data that we're observing when it comes to structural learning, then choosing a somewhat arbitrary equivalent model, it can be unsafe from the point of view of decisions that we want to make with the model that we're learning from data. So we need to be a little bit careful with how we are making these predictions in terms of the structure of the Bayesian network that we're getting. So that's what's motivating the Bayesian perspective for structural learning. And so I won't have to spend too much time on motivating the Bayesian perspective in general. And I think we're all on the same page about the advantages of the Bayesian perspective, but I want to specifically focus on the implications for structural learning. So the Bayesian perspective, what it does is that instead of finding one single graph, one single DAG that is maximizing some score, what we'll do is that we're going to, based on some data, we're going to characterize the whole posterior distribution over DAGs. So it's going to be the posterior distribution over G given the data, and then by Bayes' rule, we know that it's going to be the marginal likelihood times the prior over graph divided by some normalization constant. And so in order to make reliable predictions, what we can do is use this posterior distribution. And instead of relying on a single model, what we can do is just average the predictions that we're going to make based on the posterior distribution that we are characterizing. So that's really the objective, is to find the posterior distribution in order later on to use it to make more reliable predictions through this posterior predictive distribution. So the posterior predictive is really just taking the average of all the predictions that one can make for each possible graph, and then reweighted by the posterior distribution. So the graphs that have a higher posterior distribution are going to count more towards this average than the ones that are explaining the data less. So the pipeline for that is very natural. Once we have this posterior distribution, what we can do is just sample a number of DAGs from this posterior distribution, and then to do inference, what we can do is just do a Monte Carlo average, a Monte Carlo estimation, of the posterior predictive based on the graphs that we sampled from the posterior distribution. So all of that is assuming that we have access to the posterior distribution. But of course, the main challenge in Bayesian statistics in general is this normalization constant. This normalization constant is something which is completely intractable. In the case of structural learning, what it means is that this normalization constant just amounts to summing over all the possible DAGs, the quantity that we have on the numerator. And we saw that the number of possible DAGs is something that scales super exponentially with the number of nodes. So attempting to compute this normalization constant is going to be completely impossible. But really the key thing here is not necessarily just to get the posterior distribution, but it's mainly to sample from this posterior distribution. That's really the crucial part that we used in order to make inference down the line. And so the main question that we have is, how can we sample from this posterior distribution? We don't have to first get characterize the posterior distribution and then sample from it. If we had a mechanism that could sample from it directly, this would be sufficient to do this kind of things. And so in order to model, to have a process to sample from the posterior distribution, this is where we're going to use these new models called generative flow networks. So this is really where we're motivating the use for generative flow networks, also called GFlowNets. So I'll spend a little bit of time explaining what GFlowNets are, and then so GFlowNets, their objective is to sample from a distribution over objects. And these objects, the main thing that GFlowNets were created for is to create a distribution over discrete and compositional objects. So if we have objects that have some kind of composition and are discrete, this is really the ideal case for GFlowNets. And so I'm giving on the right-hand side a few examples of some objects that we can think about. One of them is organic molecules. So organic molecules so creating a distribution over organic molecule was really one of the first applications of GFlowNets. So the original paper was initially created to build a distribution over organic molecules. So an organic molecule, we can think about it as being multiple fragments that we are combining together to build the molecule. And it's the same thing, for example, if we're talking about protein sequences or even any kind of sequences for that matter. We can see the sequence as being just a composition of different amino acids here. In the case of inorganic material, we can see the crystal that we're creating as being a composition of different atoms and their positions in 3D space. And more relevant for us, we can see a directed acyclic graph as being just a collection of multiple edges that are connecting the nodes together. So all of these things, all of these examples, they have a discrete structure and they have some kind of composition. And GFlowNets, the way they're going to treat the sampling process is as a sequential decision-making problem. So we're going to start from an initial state. So I'm giving the example of generating organic molecules on the bottom. So we're going to start from the initial state that is on the left, which is called S0. And then at each step, we're going to add one fragment at a time. So we're going to build this molecule one fragment at a time, taking decisions on which fragment we want to add and where we want to add it. And then we're going to continue this process up until we reach a point where we have a completely formed molecule. So here, these completely formed molecules, they are represented as double circles. So we have the molecule for aspirin, the molecule for naproxen, the molecule for ibuprofen, and so on. So we're going to build these objects one at a time by by constructing them piece by piece. And so one advantage that GFlowNets have over things like MCMC is that the only thing that we need to do this generation process is to know how we're making these decisions. So when we are at any state, what's the probability of adding the next fragment to the current molecule? And so once we have that, we have the whole process to sample from the GFlowNets. One advantage over MCMC is that each time we want to sample a new object, which is going to be independent from what we saw before, we just have to restart the whole process from scratch. We restart from the initial state, build the molecule one piece at a time. We end up with a sample, and then we just reset back to the initial state and create a new sample, which is going to be completely independent from the one that we saw before. And this is really in stark contrast with things like MCMC, where in MCMC, what we need to do is construct a Markov chain, which only eventually, as it converges, is going to sample approximately from the distribution of interest, but also, and most importantly, these samples that we're getting, they are going to be correlated with one another. And so we need to do a lot of effort to make sure that if we want to have independent samples, to make it so that we're not taking consecutive samples in this Markov chain, but this is something that we don't need to do for GFlowNets. And another thing that I want to highlight is that GFlowNets, this is what I said, is that it's treating sampling as this sequential decision-making problem, and so it's very much inspired by the field of reinforcement learning. And we have some papers we have a paper recently that is showing how we're making this comparison, this connection between GFlowNets and the field of reinforcement. But so to get a little bit to give a little bit more details about how GFlowNets work, I just gave a very brief overview, but let's get into how it works in practice and the maths behind it. So what we have is a state space that is organized as a directed acyclic graph itself. So think about all of these states, all of these nodes that you're seeing on the right-hand side as being the partial molecules that we're building one fragment at a time. And so what we're doing is that we have this initial state as 0 that we're starting with. So all of this generation process is always going to start from the initial state. And then what we'll do is that we're going to add pieces up until we reach what we call a terminating state, which will correspond to elements of the sample space, things that we want to sample, basically. So in the case of organic molecules, this will correspond to the completely formed molecules. And the intermediate states, the ones that are not highlighted there, they might be just stepping stones, which are partially constructed molecules, but which have no meaning in the physical world. So the idea is to build, of a GFlowNet is going to build a process to sample from a distribution over these terminating states. And we'll see what this is going to be a little bit later. And so each terminating state will assume that they have some reward which is associated to each of them. So the reward function, the reward function is just going to take some terminating state and give us some reward associated to it. And this is just an oracle that gives us some preference for some terminating states over some others. So maybe there are some organic molecules that have a lower binding energy than others. And so we might want to encourage the generation of these organic molecules compared to others for specific applications. Then the main idea behind GFlowNets is that we have this notion of a flow. So the flow in generative flow networks, it comes from the concept in computer science of a flow network. So here, this directed acyclic graph over states that I talked about, this is creating what we call a flow network. And then when we put, once we put some flow function over that. And from an intuitive point of view, the way that you can think about flow networks is as the edges of this DAG to represent some pipes, and then you have some fluid that goes from the initial state through the different pipes up until it reaches some terminating state. And so the flow function here, which is defined for all the edges in the DAG, you can think about it as being the amount of fluid that goes through this specific pipe that is connecting two different states. So why is this flow function important? Well, in GFlowNets, we have this condition which we call the flow matching condition. And if we think about this intuitive view about a fluid going through a system of pipes, the flow matching condition is a very, very intuitive condition. It just means that if we look at the total amount of flow going into any state, is going to be equal to the total amount of flow going out of the state plus some residual, which is given by the reward R. So if we are at some terminating state, this reward R is going to have some value which corresponds to the preference for this particular state. But think about if we are not at a terminating state, if we are at an intermediate state, this reward, we can think about it as being equal to 0. And so for intermediate state, what this flow matching condition is telling us is that the amount of flow going into this intermediate state has to be equal to the total amount of flow going out of the state. So this is really what we're expecting a network with some fluid going into that to do. So that's why this flow matching condition is going to be very, very natural. I didn't say anything about how we're going to find this flow network. We're going to go back to that in the next slide. But so the main result that we have in GFlowNets is that, so this is really the main theorem that we proved with GFlowNets, is that if the flow matching condition is satisfied, so if we find a value of this flow function which satisfies the flow matching conditions for every state in this state space, then if we follow some policy, so the same way that we have the notion of policy in reinforcement learning, here it's really the same thing. A policy is just telling you what's the probability of transitioning to the next state, given that we're in the specific state. And so in our case, the policy, we're defining it as being proportional to the flow that is satisfying this flow matching condition. So if and we can think about it as just following the flow, really. Like if there is one edge which has a higher flow than another one, we have more chances to a higher probability to go through this edge instead of the other. So if we're following this policy, so if at every state we're sampling the next state according to this policy, which is proportional to the flow, then this process of generating the terminating state at the end of this process, this probability distribution, this is going to sample terminating states with a probability distribution which is proportional to the reward. So what this means is that we can characterize a distribution up to a normalization constant by just specifying what's this reward function. The only thing that we need is to find what's the flow function, that is matching, that is satisfying this flow matching condition. So really, the main question now is, how do we find this flow function that is satisfying these flow matching conditions? And so that's where we're stepping into more of the deep learning side of things. So up until now, it was very much very open in terms of just the theory of GFlowNets. But now in practice, how does that work? How can we find this flow function? So the idea is to convert this condition, this equality that we saw before, which is the flow matching condition, into an objective that we can optimize using learning techniques. So usually what we're doing with GFlowNets is that we're just taking the log of both sides, and then we're just taking the least square between the log of both sides. So really, it's a nonlinear least square objective that we're going to optimize. So here, the flow function, this f of phi, this is now something which is going to be parameterized by a neural network. So the neural network is just going to take some representation of the edge between S and S prime, for example, and then it's going to output some positive quantity which represents the flow. And then what we can do is just optimize the parameters of this neural network based on this loss function that we created. And so this expectation, it looks a lot like what you would see in reinforcement learning, and it's not a coincidence. This is really something that we took inspiration from when designing GFlowNets. The way that we're going to do that, we're going to train these GFlowNets, these flow networks in practice, is that we have the GFlowNets as this state space organized as a directed acyclic graph. What we'll do is that we're going to sample data from it. So for example, following the current policy following the policy which is based on the current version of the flow function that we're learning. Then what we can do is use this data that we acquired to compute the loss and do one step of gradient descent to update the parameters of the neural network, and then going back, acquiring more data, and so on and so forth. So this is really something which looks a lot like what you would see as a training loop for reinforcement learning. The only difference is that in reinforcement learning, the objective is just to find a sequence of policy which is going to maximize your reward. But in the case of GFlowNets, the objective is to find a policy which is going to sample proportionally to the reward function. And so GFlowNets, so just to finish on the GFlowNets side of things, GFlowNets, what we found is that there are some deep connections to other fields in statistics and in machine learning. So one of them is there is a connection to the field of variational inference. So what we're doing by treating sampling as an optimization problem, so we're trying to find this flow function as an optimization problem. This really sounds like what you would do for variational inference, and we showed in this paper that we presented at iClear last year how to do this more formally, this connection with the field of variational inference. I also worked on some connections with the field of Markov chains. So what I said before is that there are some advantages of GFlowNets over Markov chain, over MCMC, but actually GFlowNets, we can frame that under the same framework of Markov chain, and so we can more precisely compare what the GFlowNet is doing compared to what MCMC would be doing. And then finally, I hinted at that multiple times, but recently this year at UAI, we also showed that there's a deep connection between GFlowNets and the field of maximum entropy reinforcement learning. So really what we're showing is that if we tweak a little bit some of the components of maximum entropy reinforcement learning, we end up doing something which is very close to what we were doing with GFlowNets. So really, this is a very quick overview of what GFlowNets are. There's many, like way more to learn about it. And so if you are curious to learn a little bit more, don't hesitate to ask me questions during the discussion, or even send me a message, an email. I would be happy to answer more questions about that. But I want to spend the last 10 minutes talking about the applications that I've been mostly involved with, which is using these tools, the GFlowNets, in order to do Bayesian causal discovery. So we saw before the motivation of why we want to do causal discovery or structural learning from a Bayesian perspective, and now we're going to see how we can use GFlowNets to do that. And so really the idea is to build a GFlowNet that is going to sample directed acyclic graph. They're going to sample the structure of the Bayesian network that are going to be sampled based on the posterior distribution. Because remember that the objective that we want to do is to find a process which is going to sample from the posterior distribution. And so the way that we're going to construct this GFlowNet is by constructing the DAG one edge at a time. So we're going to start from the initial state, which corresponds to an empty graph with all of the random variables are disconnected to one another. And then at each step, we're just going to add one edge to the current graph. And so this new edge that we're going to add, it needs to satisfy a few constraints. The first one is that if we want to add an edge, it must make sure that it was not already present in the graph, because otherwise it wouldn't make sense to add it once again. So it's just an easy thing to check. But the second thing that we need to check is that since what we want is not to have a distribution over any kind of directed graph, but very specifically over directed acyclic graphs, we need to make sure that the edges that we're going to add are not going to introduce a cycle. And so, for example, this is why this transition from the state G3 is impossible. It's not valid to move to this state in red, because adding this edge from B to C would introduce this cycle, and it would break our acyclicity condition. And so this checking for acyclicity, checking whether adding an edge is going to create a cycle or not. This is something that sounds very expensive to do at first glance, because checking for acyclicity, even though we have some algorithms to do this, if we have to check for acyclicity for all the possible edges that we can add at every step of the generation, this sounds like very expensive, but actually what we showed in the paper is that we can actually check for acyclicity very efficiently in an online manner. So there is some quantity that we can keep track of, to make sure that we can test for acyclicity very efficiently at every stage of the generation. So this is really the structure of the GFlowNet. So how we are structuring the state space, how the states are connected to one another as directed acyclic graph itself. But now the second question is, how do we define this reward function? So the reward function for each possible state, so remember that the GFlowNets, once we've trained it, once we found the flow function that is satisfying all the flow matching conditions, this is going to generate objects proportionally to the reward function. And then if we go back to the problem of Bayesian causal discovery, we want to sample from the posterior distribution over graphs given the data. And so here, an easy way, the very natural thing to do is to define the reward function, the reward of a graph, as being the marginal likelihood times the prior of a graph. And this is something that we can assume that we can compute for every single graph. And then we can use this reward signal, training it using the loss function that we saw before. And then as we train it, as with the loss is getting as close to 0 as possible, then we'll get a distribution which is going to be as close as possible to this posterior distribution. So this was the very first work that we've done on using GFlowNets to do Bayesian structural learning. But this has a few limitations. And in particular, what I said earlier is that to compute the reward, we need to the reward was just going to be the marginal likelihood times the prior. And so it's very rare that this marginal likelihood is going to be a quantity that we can compute efficiently. And the reason for that is that the marginal likelihood, as its name is implying, is that this is a marginalization over all the possible values of the parameters that the conditional distributions may take in the Bayesian network. So we have to marginalize over the space of all the possible parameters. And so this really becomes intractable as soon as we have a non-trivial model. So let's say if we have conditional distributions which are parameterized by neural network, for example, or some nonlinear model, then this marginalization becomes completely intractable. In this case, this theta that is appearing in the marginalization, they will correspond to the parameters of a neural network, and then this likelihood term is just going to be a forward pass over the neural network. So the very few cases where the marginal likelihood can be computed analytically is, for example, if we have a system which is linear with some Gaussian noise, we can't do this marginalization in closed form. And so that was the settings that we considered in the first version of the GFlowNet for causal discovery, which we called DAG GFlowNet, which I presented before. But in the case where we have a nonlinear model, this is impossible. The solution for that is to, instead of just looking at what's the posterior distribution over the structure alone given the data, what we'll do is that we're going to look at what's the joint distribution between the structure of the graph and their corresponding parameters of the conditional distributions for the Bayesian network together. So the joint distribution between the two. Because now what it means is that this posterior distribution, if we still use Bayes' rule, this is now equal to the likelihood, so not the marginal likelihood anymore. We know what's the values theta of the parameters. So the likelihood times the prior of the parameters times the prior of a graph. And all of these quantities, we can compute them for any kind of models that we can use for the Bayesian. And so this was the idea that we used for this extension of DAG GFlowNet that we presented at Paris last year, where what we did is that instead of just having a GFlowNet to sample only the structure of the Bayesian network, what we did is that it sampled the structures of the Bayesian network and the values of the parameters for the different conditional distributions appearing in the Bayesian network. So this is what allows us to apply something like GFlowNet to model nonlinear causal relationship. And so the idea of the way that we structure this GFlowNet now is very much inspired by what we saw before, and it operates in two phases. The first phase is exactly what we saw before. So we're going to build the structure of the DAG one edge at a time. So we're starting from the empty graph and adding one edge at a time. And then now once we are happy in a way with the structure of the graph, instead of just returning it, we're going to move to a second phase, which is going to condition on the structure of the DAG. We're going to sample the parameters of the different conditional distributions appearing in the Bayesian network. So this is really the second phase, which is novel compared to what we saw with GFlowNet earlier. And so this is an interesting problem, because this first phase of the GFlowNet is really over the discrete quantity. This is a discrete structure of the Bayesian network. But really, the second phase is a continuous quantity. These are the parameters of the conditional distributions in the Bayesian network. And so all of what I said so far about GFlowNets and how we can use them to generate objects which are compositional but mostly discrete. What we showed also in some paper is that some of these ideas, we can also extend them to continuous state spaces and also to hybrid spaces with discrete and continuous components. So this is really what's the strength of GFlowNets, is that this flexibility to create a distribution, to have a sampling process over very complex sample spaces. This is something that you would have a lot of trouble to model with MCMC, for example. So that's really one advantage of GFlowNets, is this flexibility in what we want to model, what we want to sample. Sorry. And so now again back to the original problem. I talked about the structure of the GFlowNet, how the states are connected to one another, and then the way that we're going to define the reward function. Recall that the objective is to sample from the joint posterior distribution, and so the reward for a particular graph and a particular value of the parameters theta is just going to be this product that we can compute efficiently for any kinds of parameterization of the Bayesian network, even if it's a nonlinear model, because the likelihood is just a forward pass of a neural network, and then the priors are usually something which is fairly easy to compute. So this is really the idea behind using GFlowNets to do structural learning over very general Bayesian networks. And so we also have some we have some experimental results. I won't spend a lot of time on it because we're getting close to the end. But really, what we showed is that on very small systems where we can actually compute what's the target distribution, what's the exact posterior distribution. So we can only do that for very small system. What we show is that we have a very faithful approximation of this distribution based on the GFlowNet. So here we're comparing what's the probability of some marginal probabilities for some quantities of interest, either computed with the exact posterior distribution on the x-axis or estimated with the GFlowNet. And so we see that we are very close to the diagonal line, meaning that these two quantities, either from the exact posterior or the GFlowNet, are very close to matching. We also have some more specific metrics that we looked at for the problem of structural learning. So in the case of so we're looking at, for example, what's the performance of something like GFlowNets or compared to other methods that are existing in the literature to also do some Bayesian structural learning. How well does that perform in terms of negative log likelihood over some unseen data. And so what will the hope is that the models that we're getting, the models that we're sampling with the GFlowNet are going to be as low as possible of negative log likelihood over some unseen data. So we're doing that with linear Gaussian models, but also for nonlinear Gaussian model, which is something which has been very much. There's not a lot of work specifically looking at this context of having nonlinear model for the Bayesian network. So that's why we have very few points of comparison. And we can also look at just specifically not having to compare against other methods, very specifically how faithful is the approximation of the GFlowNets. So this is the figure that we have on the right-hand side. In terms of the probability, the log probability estimated by the GFlowNet compared to the log joint distribution between the data, the graph, and the parameters. Because ideally, what we want is to have a linear fit between these two quantities, because the log probability of the GFlowNet has to approximate this posterior distribution. So that's what we're seeing in this synthetic setting. But we also experimented with some real-world data coming from proteins, coming from inference over protein signaling networks. So now the data is the expression of different proteins that are inhibiting or activating some other proteins in some network. And so what we can see, we're making the same same kind of analysis. That's what I presented before. And what we can see is that the fit is very linear between these two things, suggesting that the GFlowNet is really an accurate representation of the posterior distribution. That's it. Thank you. So these are all of my collaborators. I presented a lot of things about Bayesian causal discovery, GFlowNets, and how we can use GFlowNets to do Bayesian structural learning. And thank you again for inviting me to this group meeting, and I'm happy to take questions now.
Thank you so much, Tristan. Could everyone unmute their microphones and give Tristan a round of applause? So that was really interesting stuff. I guess now we can move to questions, discussion, comments. So I don't have access to the chat, so I don't really know if there were any questions during the talk, but yeah, just feel free. Yeah, Chris?
Yeah. Thanks for that was a brilliant talk. That's the most clearest explanation of GFlow networks I've witnessed. That was really, really helpful. Thank you very much for that. And really, really interesting stuff as well. So, so obviously these combinatorial spaces are large, and you're still doing some kind of random walk through those spaces, right? I mean, when you're initially, and so is there an assumption about the smoothness of the reward function, right? Because it might be some specific structure of graph in these systems that's which you've got the highest reward, and then the signal, there's some very poor signal to get there or something, some kind of island. So is there an assumption of the smoothness? So close by graphs, there's this gradual increase in their reward.
So this is
the posterior. I'm thinking more of the previous things rather than the posterior, but I don't have to translate that.
Yeah. So this is a great question, and this has actually two answers. So in theory, no, we don't need any kind of assumption on the smoothness of the reward function, because it can this theorem that I presented about GFlowNets, it holds for any kind of reward function. It really, we can have a very two very close states, like one state and then the next state, that have very, very different, a wide range of different values for the reward function, it will still get something which is sampling proportionally to the reward if we find this flow function that is satisfying these flow matching conditions. So this is something exactly as you said, like in the context of posterior distribution, if we have a lot of data, this posterior distribution becomes very peaky at some part in some parts of the space, and so we have a reward function which is taking a lot of a wide range of different values, and so we are losing this smoothness. So in theory, it's not a problem to have this non-smooth reward function. In practice, though, it is a problem. So it is a problem very specifically because we're using neural networks to approximate all of this. So the neural network, it has to handle these very large changes in reward function somehow when we are trying to minimize this loss function, because we need to make sure that okay, all of these conditions are going to be approximately satisfied. And so if we have a very small reward followed by a very large reward, and the neural network needs to take into account these very large changes in reward function. And this is not something that we can solve with our usual toolbox of deep learning. So in deep learning, usually if we have very different ranges of values, what people would say is that, well, just normalize your rewards. But now the problem is that here, if we're normalizing the rewards, we're changing the distribution that we're approximating. So really, it is indeed a problem, this non-smoothness of the reward in the case, but just from a practical point of view, we're just getting a poor approximation of the posterior distribution if we have a very large data set. So this is the settings that we experimented with for causal discovery. I think we had no more than a few thousand examples in our data set. I think if we move beyond that, we're just going to hit these problems from a practical point of view. And there's a lot of, I think there's a lot of open research in there, like how to actually make these neural networks handle these like very deep variations of reward. And so there's a second answer to this question, which is that it's not so. This is you're exactly right that it's really a kind of a needle in a haystack problem where we have such large spaces and we need to find the regions of the space which have higher reward compared to others. And so this is not necessarily a problem with, well, it is somewhat a problem with the smoothness of the reward function, but it's mainly a problem of a classical problem of exploration. And so we were facing exactly the same problem as reinforcement learning when it comes to exploration. We need to find some clever way to explore the state space to go towards parts of the space that are more promising than others. So right now the research in terms of GFlowNets is kind of catching up to reinforcement learning. We're slowly adding some of the tools that reinforcement learning has been implementing back into the way that we're training our GFlowNets, but this is very, very slow, and so there is a lot of opportunity just to know how to be more clever in terms of exploration of the space.
Cool, thank you very much. Great talk, thank you.
David?
Hey, can you hear me?
Yes.
Yeah, thanks, Tristan. That was really great. I'm very informative. So I got kind of interested in the detailed balance assumption that's being made in the GFlowNet equation. I was wondering whether there's like sort of like an analog when we're moving from, because like detailed balance is kind of like equilibrium statistical physics picture. And I was wondering, is there like an analog to non-equilibrium picture where you sort of break detailed balance and maybe you're trying to model non-stationary distributions. So I was wondering if anyone has worked on that or thought about that.
So now that I know of this, like studying how breaking the detailed balance assumption is, how does that affect the distribution that we're getting? I don't think there's anyone who has worked on that, but something that I should also mention. So I didn't talk about detailed balance, but essentially the condition that I presented today was really just to give this intuition of what GFlowNets are with this flow matching condition, because it's from a, let's say, from an intuitive point of view, this view of having pipes and fluid going through them, it's a little bit more visual, but this really is not the way that we're training GFlowNets anymore. This was really the original paper that introduced that, but nowadays we're based the conditions that we're using that still give you the same guarantees about sampling proportionally to the reward. We have some more modern versions, and one of them is what we call the detailed balance. So that's what David was referring to. This detailed balance condition is not exactly the same kind of detailed balance that we're seeing in the literature in MCMC. And it's really, it is just inspired by the literature on Markov chain, but this is not exactly this is not exactly the same thing. And the reason for that is the condition is, the detailed balance condition is kind of the goal that we want to achieve, but it's not an assumption that we make from the beginning. So in MCMC, usually what we say is that we have a Markov chain, and we assume that this Markov chain satisfies this detailed balance condition. We're building a kernel, like for example, based on Metropolis listings, that is satisfying these detailed balance condition. In our case, what we do is that we have something which is very analogous to the flow matching condition. This is an ideal situation that we want to achieve. This is what we hope that all of our transitions in the GFlowNet are going to satisfy the detailed balance, but we're just going to approximately satisfy these detailed balance because eventually what we'll do is just learn the parameters of a neural network to approximately satisfy these conditions. So all that to say that maybe this off equilibrium that you're mentioning, we're very much in this situation all the time when it comes to GFlowNet, because what we do is we're just approximating this detailed balance, but we're never going to be exactly matching this detailed balance. Like, this is the hope that we want to achieve, but we're not going to exactly satisfy that. So, of course, this is going to induce some level of approximation in the distribution that we'll get in the end. It's not going to be exactly proportional to the reward. There's going to have a little bit of error coming from the fact that these detailed balance conditions are not quite satisfied. But that's very close to this setting that we saw with the flow matching condition as well.
Great, thank you.
Cool. Alex? Oh, you're muted, Alex.
Yes. Thanks. Hi. Thanks a lot for the talk. It was great. So I just have sort of a very practical question about generalization if you're training this on generating like Bayes nets. So like I was looking at the first paper where you just learned the structure, not the distribution. And you know, there's this example of training on random graphs with like 5 nodes or something. So I'm just wondering, empirically, like how well does this generalize to networks of different sizes? Or are there any tricks you have to do to make that work?
Yeah, so that's a great question. So in the first paper, we experimented. So this very small these experiments on small networks. That was like only to verify that GFlowNets can actually accurately approximate the posterior distribution in an ideal setting where we can compute the posterior distribution. But of course, once you move to, let's say, 7, 8, 9 nodes, you won't be able to compute this posterior distribution in closed form anymore. So we need some other metrics. So that's what we've been looking at in the paper. So we went all the way to systems of size up to 15 nodes. And so we're just testing some metrics which are very specific to the literature on Bayesian networks. So things related to the structural Hamming distance. So how close are we to the structure that we used in the first place to generate the data? So we can compare how close the data, the graphs that we sample are from this ground truth graph that we started with. There are some other metrics that are looking at more the presence of edges compared to the ground truth graph. But these metrics are really not ideal. So all of the metrics that we used in the original paper, they have some like very heavy drawbacks, and I can come back to that if anyone is interested. But all of that to say that we tried to, like in the second paper in this extension that I presented, we experimented up to on systems up to 60 nodes. And then we had, so I was working with some students that made it work to, let's say, 100 nodes, maybe 200 nodes. Beyond that, we don't know. So ideally, we want to use these tools to maybe apply them to biology, where we have systems of multiple thousands of nodes. We're not at this stage yet. We're not close to that. And the major challenge for when it comes to scaling up these to scaling up to more nodes is that so there are two main challenges. The first one is what I talked about before about exploration. So now if you have a larger system, you have a much larger state space over which you have to to find the regions that are most promising, that have the higher reward. So having an exploration strategy which is more which is smarter than the ones that we've been using, which are very naive in comparison. This is something which is essential. The second, like the corollary of that, is that we need to scale up also the neural networks so that we have the flexibility in terms of the flows or the policies that we're representing in order to make sure that these conditions are going to have some solutions with the parameterization that we're using. So these are more on the, let's say, practical side of things. And then there's the second challenge, which is how do we make sure that what we're doing actually makes sense? So when we scale up to very large graphs, we are running into the issue of, okay, we get a process that is sampling some DAGs, but how can we make sure that this sampling process is actually close to the posterior distribution? The samples that we're obtaining are faithful for the posterior distribution that we're trying to model. So this becomes very challenging as we scale up. We have this region on small systems, so with 5 nodes, where we can compute the posterior distribution, and then we can do the exact comparison between the exact posterior and the GFlowNets. Then there's a range of medium-sized graphs where, like, up to, let's say, 20 to like 20 nodes, we can still do that, where we can actually do this this linear fit comparison that I was talking about, which is at the very end. So this one on the right hand side, where we can check if the log probability of certain samples from the GFlowNet is linearly correlated with the log reward. So this is something that we can still do for graphs of about like 20 nodes. Beyond that, that's very open. So the best thing that we can do is just in terms of negative log likelihood on held out data. So if we're given some new data, see how well this models how well the graphs that we sampled with the GFlowNets are modeling this this unseen data. But this does not guarantee us that these graphs that we're sampling from the GFlowNet are anywhere close to being related to the posterior distribution. So really the main challenge that I see with scaling up the size of the system is in the evaluation, making sure that we're actually doing something that is meaningful.
Oh, thank you so much. That was really, really helpful answer. Thank you.
Thanks, Tristan. Do we have other questions or comments? Yeah, David?
Yeah, so another thing that I really liked was this sort of two-phase approach to sampling from posterior. And I was wondering whether a similar idea could be used for also inferring the number of nodes in the graph to begin with, because at least my understanding here is that the DAG is a fixed number of nodes. But could you do a similar process where, first of all, you figure out how many nodes are in the graph, and then you infer the structure of the graph itself?
Absolutely, yeah. This is definitely something that is possible with this framework. The reason why we made this assumption that we know the number of nodes in the first place is that what you start with is a data set, and the data set has a certain number of columns, a certain number of features, and so we know with this number of features how many nodes we have in the system. But let's say if you want to apply that to a setting where you want to learn a Bayesian network over a latent variable model, now that's where you may want to have a system that let's say a mechanism that can automatically give you how many nodes you need, how many nodes you have in your latent variable model. And this is definitely something that you can do with this framework. It's just going to be another type of action. So it could be, as you described, we can first decide how many nodes we have, and then the second phase is the structure over these nodes, and then the parameters. Or what you can say is that this first phase can be a mixture of adding either edges or adding nodes, and then you can have this flexibility as well to do both of these things at the same time during this first phase. So the way that you're let's say designing the structure of your GFlowNets is really up to you. Definitely a very good idea.
Great, thank you. And just a quick follow-up on that. So do you have any intuition for which of those two approaches would work better in practice? Sort of the hierarchical versus just combining nodes and edges into the single first step?
That's a great question. I don't have any intuition of whether like one solution is going to be strictly better than the other. Definitely the solution that you're describing is going to be easier from just a implementation wise, because you can clearly separate these three different pieces, and you don't have to, let's say, tweak the way that you can add either edges or nodes at the same time. This might be something which is a little bit more difficult to implement in practice. So just from a practical point of view, I would go first with the option that you're suggesting. But I don't know if it's going to necessarily be strictly better from from an optimization point of view, and then the final performance that we're getting.
All right, great. Thank you very much.
Cool. Yeah, I was wondering, so it would be quite cool to use GFlowNets to infer the world model of an agent. Say I mean, if we consider like hierarchical POM-DPs to say, oh, we're going to add a layer and add another layer and so forth. I have some notion of uncertainty that we can then exploit for decision making. Do you have a sense of to what extent this would be feasible? And also whether GFlowNets would be a good approach? And the reason I ask is because when we have an agent, we want to be able to operate in real time as data comes in. And we need to be able to do things online. So my sense is that we would need to retrain the GFlowNet every time after a new batch of data to get a new posterior over the world model. On the other hand, I feel that the posterior with the GFlowNet would be pretty expressive, which is pretty good. So I just want to hear your thoughts.
So I think definitely it's a good idea. Of course, I'm going to sell GFlowNets, so I need to say that it's a good idea. But I genuinely think that it's a good idea because when it comes to world models, this is something that is discrete in nature. And so this is really where GFlowNets particularly shine. So I think it definitely makes sense to use a GFlowNet to, in that case, to learn a distribution over world models. Now the question of how to do that in practice. So this, I completely agree with you that since you have the agent is going to acquire the data, and then let's say the feedback for the GFlowNet is going to depend on this new data that is acquired. So in other terms, if we take the let's say the namings of GFlowNets, the reward function of the GFlowNet is going to depend on the data that is coming in. And so we would need to retrain the GFlowNet with a new reward function every time we change the data. So I agree with you that this is where like it can be limiting to if we have this kind of bi-level approach where we have the agent gathering data and then we have the GFlowNet being trained multiple times. What I would say is that hopefully as we go, the updates of the GFlowNet will be, let's say, you won't have to update the GFlowNet as often, like for as long as what you have in the initial phases of training. So as you go, probably it will be quicker and quicker to have these training phases of the GFlowNet. So maybe that's one hope for that. There's another thing that I want to mention is that there are some other works that are looking at how to train a GFlowNet with a learned reward function as well. So this is probably some directions that are worth looking into in this setting, and it's in a very different application domain. They were looking more on the let's say training a generative model based on some data, and so they had some reward function that was depending on the way that we were basically it was depending on some energy function that they were learning from data. So they had also this idea of the reward function for the GFlowNet was something that was also trained. So in the way they managed to still do it, where they were training the GFlowNet and training the reward at the same time. So there are ways to have, not necessarily like have all of the data acquisition and then all of training GFlowNet, and then just interlacing these two phases together. There are ways to do both of them at the same time. So this could be also an option for this setting, and you would have something with a little bit more quicker, with a little bit quicker feedback for the agent.
Right. Yeah, that's super interesting. So just a quick follow-up. Is there, so I look here at your phase 1, phase 2. Is there, so could it be possible in an agentic setting to do phase 2 very often? As new data comes in, you would update the states and parameters of your model, fairly often at a high resolution. And then at a much lower resolution, you would update the DAG. Does that, do you think that would work?
I think so. I think so because I think it makes a lot of sense to have different frequencies of updates for different parts, and especially if we don't start necessarily from scratch, but from, let's say, something which was more or less good enough for the knowledge that we have acquired so far, all of the data that the agent has seen, and then it's going to change maybe the let's say the parameters maybe more frequently than the DAG itself. So definitely this is something that can be done, and these are just parameters that these are different parameters of different neural networks. So we can really have this flexibility of choosing when to update ones compared to another. So yeah, that's definitely possible and a good idea, I think, in general.
Cool. Thank you very much. Do you have any other questions or comments? So it looks like no. But now I'm going to hand the floor over to Carl if he wants to say a few things. Do you want to say a few things, Carl?
Yes, I want to. Yeah, I do. I want to say a few things.
Please go ahead.
Well, let's have the. Can we have the slides back? Because they were brilliant slides and usefully scaffolded.
No problem.
And that was really brilliant, Tristan. I think, I think I can speak for everybody that we all really enjoyed it.
Well, thank you for attending. That was really nice.
Yeah, I did, just to reiterate that it was extremely clear, very informative. So a lot of the magic and mystery of GFlow networks has now been resolved for a lot of us. So thank you very much for that. And of course, that opens up a whole range of questions, I think the majority of which you've already very fluently addressed. I'm going to ask some very simple-minded questions because this is quite new to me. Also with an ear to the themes that you've already been discussing. There were quite a number of them, so I'm going to forget some, but just to come back to, I think it was Alex's question about the, or possibly Chris's. So if I understand this, from the point of view of the GFlow network itself, this is a DAG, and the nodes of the DAG stand in for combinations of edges on a Bayes net. And the question that you were addressing was, well, if you have large numbers of nodes, say 100 nodes, then the nodes on the GFlow DAG will be very, very large in number. And you were saying that some people have got up to nearly 100 nodes on the Bayes net, which I imagine corresponds to the billions and billions of nodes on the GFlow DAG. But presumably, so this is a question, presumably you have some hyperpriors about the nature of the Bayes nets that would certainly induce a sparsity on the causal, on the edges in the Bayes net, which must place some upper bound on the number of nodes in the GFlow DAG. Is that something which, and in principle, one could also optimize those hyperpriors in relation to your score functions or the ultimate average model evidence or marginal likelihood?
Yeah, so this is definitely something that you can do, and I don't know if that exactly matches your idea of hyperprior, but one thing that an easy way to reduce drastically the number of nodes in the DAG of the GFlowNet is to say we want to limit the number of the number of parents each node can have, because right now we have, like, each node can have a lot of parents, but we know that in practice, well, not in practice, but in the real world, probably if you have if you observe something, this is not going to be caused by every single other parts of your system. It's probably going to be caused by very few components, and this goes back to your idea of sparsity. So what you can say is that I want to generate the structure of the Bayes net, but with the constraint that each node has at most three parents. And so this reduces already from something that grows super exponentially to something that grows in polynomial with the number of parents. So this is something that is definitely possible, and within the framework of GFlowNets, this is something that is extremely simple to encode, because what we can say is that if in this, so going back to this first figure, what I was saying is that we need to, when we want to add an edge to the current graph, we need to check if it's already there or if it introduces a cycle. We can add a third condition, which is, does this edge add like exceeds the number of parents that this node is going to have? And then if it does exceed, then we just consider that action to be invalid, and we're not going to consider that anymore. And this is going to prune like a significant amount of the nodes that can be reached with the GFlowNet and the distribution over which we define this posterior.
Excellent. Yeah. So one could paraphrase that by saying you're putting the plausible sparsity constraints in terms of the in degrees on the adjacency matrix, or on the graph itself, and presumably one could also apply that to the out degrees. And I'm thinking here just from a theoretical perspective, those in a sense define the Markov blanket, and there are emerging proofs that with probability 1 you get lots of Markov blankets as the system size grows, which does imply a constraint on the in degree and the out degrees, which I'm sure you could leverage. Can I just ask? I mean, there's been great emphasis on DAGs. So you don't like circular causality or loopy graphs, then? They're not.
Well, it's not that I don't like them, but it's more because this is the standard framework that people have been using for Bayesian networking in general, but also for causality. Because if you want to do this extension from standard Bayesian networks to causal Bayesian networks, now these edges in the directed graph, they have some causal meaning. So if you had something like a cycle, it would mean that there is something that causes something that may cause this other thing. So there's like loopy causal relationships, which are somewhat unnatural from a modeling perspective. So I think that's why people like Yuda Pearl very early on were very, very much focused on the acyclicity constraint. And so that's why I use this myself, but I have nothing against cyclic graphs, and actually moving forward, cyclic graphs are probably things that are going to be necessary one way or another, because one direction for the application of these tools is to apply these to biological networks. So that's one example that I presented was on protein signaling network, but also for gene regulation. So how genes are interacting or activating with other genes. And so beyond just the simple reason that I said earlier, where these are systems that are extremely large and this is already challenging. The other thing is that from a modeling perspective, it's very unlikely that biology has no cycles because there are feedback loops everywhere. So if you have a gene, it's going to cause the activation of the gene, but also like it's going to inhibit maybe some other process that is activating the first gene that you had. So you have feedback loops everywhere, which are not modeled properly with the directed acyclic graph, and so you can actually move to cyclic graphs. There's nothing preventing that from a modeling perspective with the GFlowNets. And actually, there are some other papers doing exactly that, doing this using similar ideas as the ones that I presented today, but quote unquote extending them to cyclic graphs. So definitely possible. It's just I was bound by the literature on
Right.
Bayesian network, which is focused.
No, sure. Yeah, and as you noted, some of this inherits from Judæus Pearl's analysis of causality. Just to endorse what you just said, in my world, causality comes from dynamics in real systems, where circular causality is a rule, not the exception. So you talked about gene-gene and gene-protein interactions, but of course, in neuronal networks, in the real, not neural, but neuronal networks, there's an enormous amount of circular causality. So it's, I'm pleased to hear, because I could see nothing which required a commitment to DAGs in this mechanics. It would seem to handle any arbitrary causal structure. Excellent. Well, perhaps it's pursuing that. If you time unfold a dynamic Bayesian network, that now becomes a DAG. So presumably you can also apply this to dynamic Bayesian nets.
Exactly, and the work that I was talking about before, where they extended these ideas to cyclic graphs, they do exactly what you're describing. They're just unrolling in time a dynamic Bayes net, and so now you're back to a setting where you have acyclicity. So all of the tools that I talked about are still valid. It's even simpler because this second condition where we have to check whether adding an edge is going to introduce a cycle or not. Well, in the case of unrolling a dynamic Bayes net, it's never going to introduce a cycle, so we can just keep on adding edges from time step t to t+1 to certain nodes, and there's nothing wrong about that.
Brilliant. And to come to the question about detailed balance, and what I was just wondering is how you'd break detailed balance in this system from the point of view of the GFlowNet. And I would imagine, well, first of all, let me ask, I'm assuming that the GFlowNet could be articulated in terms of a master equation or a Fokker-Planck equation, where you're now treating the water as probability mass and you're just diffusing it around. But the peculiarity of the GFlow structure is that it's a driven system. So presumably you're pumping in mass or water or probability mass at S sub 0, and then there's a sink, which is your reward, and you're now the equilibrium is now articulated in terms of that flow condition that you wrote down. So from that perspective, I mean, that is a dissipative system, even though it is an open dissipative system because it's being driven by S sub 0. So I'm just thinking, how would you make it non-dissipative? And how would you break detailed balance in a sort of physics sense? And why would you want to do that? And I'm just wondering, at the back of your mind, were you talking about the capacity to use the turbulence, the solenoidal dynamics that you get, the itinerancy that you get when you have non-dissipative dynamics as part of this exploration, to explore corners of the flow that you wouldn't normally go to? And I'm wondering whether you need to now use sort of reverse diffusion, as it were. You're actually unassembling and unadding, so that you've got the opportunity for sort of circular flow around the network. Because at the moment, I sort of have in mind a big master equation with the state transition matrix, everything being below the leading diagonal. So you always have to move forward, if you like. You're always flowing to an endpoint, to your sinks that are being reinforced. But to actually get that sort of break detail balance, to get a non-dissipative flow, you'd actually, to get turbulence, for example, or like stirring a cup of coffee, to do that right kind of exploration, or to have a exploration for free, you'd actually need to have the flow going in the opposite direction. So the upper triangular part of the transition matrix was populated. Is that something that and I can't see why that wouldn't work. You're just allowing for things to flow backwards and forwards, and in principle, they should still satisfy the same flow constraint.
Yeah, exactly. And so what I said earlier is that one of the works that I did last year was to connect GFlowNets with the literature on Markov chain, and it's exactly answering this question that you had, and the way that we reconcile this idea of forcing flow into the flow network, and then into the source of the flow network, and then eventually going out in the sinks, and then this master equation that we usually see in Markov chain. It's very simple. It's just we're taking the source, we're taking the sink of the GFlowNet, and then we're just like connecting them together. And so by connecting them together, we do end up with this master equation where we do have the let's say the flow. So now it's a different object. It's not the flow at specific over specific edges, but it's the flow going through states. And so this flow going through states, it needs to satisfy this master equation, which basically it's just a conservation equation. It's the flow for each state is going to be equal to the flow, the average flow of the parent states averaged over some transition probability, and so that's the transition probability that you would see in Markov chain. So I think this is answering part of your question, at least. How can we reconcile these two views of pushing the flow, and then I guess that's what you meant by master equation. And then in terms of breaking the detailed balance, so maybe there are some different kinds of detailed balance, but the way that I see detailed balance in the context of Markov chains for MCMT, it's more we need detailed balance to ensure something like ergodicity at the end of the for the chain to actually enable this convergence to the target distribution. Whereas in the case of GFlowNet, we don't need ergodicity, and the only thing that we need is to have something which is recurrent, but which is irreducible, but like in this view of let's say connecting together the final state and the initial state. So we just need something which is irreducible, but with a very specific structure. And so this is where the I haven't looked too much at the detailed, let's say the connection between the detailed balance as we have that for GFlowNets, and the detailed balance that we see for that we use usually for Markov chains. I haven't looked at the exact connections that exist between the two, But I'm definitely curious about this, and especially about what you're saying about this. Let's say this swirls that we can use to naturally get some exploration. This is definitely something that I would love to discuss more, because this sounds like a principled solution for like a major challenge that we have in GFlowNets that I don't think anyone has been thinking about, at least that I know of.
Yeah, I think there is an emerging, well, probably when I say emerging, it's probably been around for decades and decades. But you might find something under solenoidal mixing as a way of optimizing the exploration of phase of some search space or phase space. Solenoidal mixing. But you're absolutely right. There will be a non-equilibrium steady state, but it will. My favorite example is, if I want to optimize the solution of my sugar in my coffee or my cream in my coffee, I don't just wait until it all flows to the bottom, or I have to mix it up to get that equilibrium on an equilibrium steady state. So that's the essential idea, and it seems to fit very comfortably with the way that you were describing. So I was actually reading detailed balance as the solenoidal free sort of rushing from the source to the sink, whereas you could introduce a bit of solenoidal mixing, which might interestingly mean that you have, in your sampling scheme, you have to take the average over the cycle of the mixing in order to get a sort of a more ergodic or wide sense stationary sample. But it should in principle explore efficiently all the state space. I noticed Lance had his hand up. Now it's gone away again.
Yeah, I just had a clarification question, but you clarified it, Cal. So yeah, thanks.
Good. Can I ask a very detailed technical question? Your objective function for the GFlow, so you've got a square of a log.
Yes.
Who invented that?
So initially it was introduced because intuitively what we have is that the magnitude of the flows are going to be very different between what you have at the very beginning of your flow network and at the very end of your flow network, because ideally your flow at the very beginning should gather all of the flows that you'll have downstream. So the reason why there was this log in the original formulation was because of these differences in the scale of the magnitude, sorry, of the different flows that could appear even at the level of just at the level of a single state. So that was the historical reason why we were using log, and we've been using logs for, let's say, the detailed balance condition and another type of condition which we call trajectory balance condition, which looks at complete, like some conservation law at the level of complete trajectories. We still have this log, which seems a little bit like legacy from old times of the initial paper of GFlowNets. But actually, there is an interesting reason why this log appears, and it's natural. It can be naturally explained through the lens of this this connection that we established with maximum RL with maximum entropy reinforcement. So really, in the case of this, so I can't talk exactly about this the flow matching condition and the loss associated to it, why we have a log. But let's say if we look at the detailed balance condition, so if we take detailed balance and then we take the log of both sides, and then doing the same exercise and taking the squared difference of the logs of both sides. So this is what we get, something which is called the detailed balance loss in GFlowNets. And what we showed in the paper that we presented at UAI this year is is that detailed balance loss for GFlowNet. This is exactly, and with this log appearing in the loss for the detailed balance is exactly the same as the loss for an algorithm which is called soft Q-learning, which is just the Q-learning version in the maximum entropy reinforcement learning version of the standard Q-learning algorithm. So really there are very deep reasons why we want to use the logs, not just from legacy perspective. It's really coming from this these connections with RL.
Yeah, and I'm just wondering whether there are even deeper connections. You sound very pleased with the connection with RL. In my world, that's not something to be proud of. But it would be terribly interesting and deep if you could show a connection with, say, fluctuation dissipation theorems, or the fact that you've got a log there because effectively you're looking at a relative entropy or a KL divergence or across, a relative entropy. That speaks to the maximum entropy part of your RL. I suspect the reinforcement part is irrelevant. It's the entropy.
It is mainly the entropy.
Yeah, and I'm just wondering if the functional form of your score function could at least be heuristically motivated by by an analysis which has looked at the information theoretic or the relative entropy, or minimizing the a particular KL. But the square is interesting. It reminds me of measures of information length when you're converting a KL divergence into a distance measure. That you have to take that sort of that square to get in there. There was another reason I found that interesting. I can't remember what it was now. Never mind. But thank you. That was it's a really interesting. Why does that work? I'm sure that you will get that. It would be really nice to find that functional form emerging from other perspectives. Other perspectives on that.
Absolutely, and this is fascinating. All of these connections with other fields. This is something that that was driving a fair part of my PhD, and I was like I love finding connections with some other fields. And so if there's any other thing that could also be connected with the actual functional form of the losses that we're using, that would be even better. So yeah, thanks a lot. That's fascinating.
Right. I suspect you already know about it. If you don't, I find the work of Seifert on fluctuation dissipation theorems, which deal with stochastic thermodynamics, but basically they're talking about noisy stochastic paths through certain phase spaces. And what he shows is that there are very generic, almost universal or master integral fluctuation theorems. And it's looking at your setup and some of the functional forms of the equations. There might be some fundamental connection there. So it's stochastic. It's like statistical mechanics, but it deals with one particle. So it'd be like one sample from your GFlowNet.
Mm-hmm.
Anyway, that's a distraction.
Very interesting. Definitely, this isn't something that I am not aware of. So I would love to go in more in details about that. Yeah. Thank you.
Well, yeah, it's probably summer reading or weekend reading. But if you have the time, then it's Seifert, SEIFERT. U is his initial, and he's written a lot. If you find something on sort of master fluctuation equations or stochastic thermodynamics, just scan the equations and then spot the ones whose functional form you like, and then just do a bit of reverse reading to see where they came from. It's you might find something there. Just one final question: can we go back to the now turning to the causal discovery? And I just wanted to ask. Well, I got one question of a very technical, silly nature, and then one sort of more abstract question. It was just the difference between the phi's and the theta. So I understand the phi's to be parameters of the flows or the probability transitions at the level of the GFlow network. And now the thetas then are basically what they're parameterizing some likelihood mapping from the states on my Bayes net to some data, or something more complicated than that? I didn't quite understand the role of the thetas there.
That's right. So the thetas are the parameters of the Bayes net. So if we go back to, if it doesn't take too long, here. So the thetas in all of what I was talking about are the parameters of this Bayesian network model. So these are the parameters of each conditional distribution. And then, as you say, the phi's are the parameters of the neural network parameterizing the pros.
I see. I see. So the data gets into the game because you assume that you've got some data being generated by each of the nodes on the Bayes net, as opposed to treating them as latent states or hidden states. That you've got some empirical access to at least some of these.
Exactly. Yeah. So we do have direct observations of all of the random variables in the system. We are working on an extension to learning to doing the same thing over latent variable models. So based on some high-level data, some low-level data, sorry, and then having some learning the structure of over latent variables that we need to also infer. But this is ongoing work, and this is very difficult work. So the step between just the first paper on with the marginal likelihood to including nonlinear model through modeling this theta was a step, but it was achievable. Here we're talking like moving to adding latent variables on top of it happens to be like a very steep step from there. So like from a theoretical point of view, it doesn't change too much, but practically speaking, from an optimization point of view, it's much more challenging.
Yeah, and I imagine it's because you've now introduced continuous variables into the GFlow machinery, which is
exactly. Yeah.
Can I? So that brings me to my final question. And can we go back to the nice slide where you're showing the problem of the marginalization? So when I looked at that, so I think it's about the 5th slide. Yeah. So when I looked at that, I thought, well, why don't you just use a variational free energy or elbow on that one? Why don't you use an approximation to the marginal likelihood of the data given the graph? As opposed,
you definitely could. You definitely could use an approximation of the marginal likelihood. This is not something that we've looked into. The reason why I was a bit afraid of adding another layer of approximation is that we're already approximating the posterior distribution, and so adding another layer of approximating effectively the reward function that we're using, I was a little bit afraid of this compounding effect of approximation over an approximation. But this is definitely something that would be worth trying. And,
I mean, it would. If that's the case, then that would really take the pressure off the numerics of having this joint distribution for your RG flow over these potentially high numbers of discrete states, but now a whole bunch of continuous dimensions, which I imagine you don't really. So just from my point of view, the way that the good approximation, which takes the pressure off the numerics, is a mean field approximation where you assume conditional independence between G and theta, and that's effectively what you would be leveraging if you now just used a variational approximation or bound on the, well, it'll be the log marginal likelihood of D given G. And this would be just effectively variational Bayes with 2 steps. One step would be the effectively optimizing the thetas using some standalone technology. Could even use neural networks and amortize that, but then leverage the conditional independence between the thetas and the G's in order to then get your GFlow machinery just focused on the discrete state spaces. That was the motivation for my question.
Yeah, and so interestingly, I should also mention that we do have a paper. So this paper that we presented at NeurIPS last year, it was after we had this development of using where we proved that we could use GFlowNets over continuous spaces. But even before that, we already wanted to apply these tools to nonlinear models. And so we had an initial paper with the same author that are here, where we're doing very close to what you're describing. We're treating this as a variational based problem. Variational with a variational based algorithm. And so we are just looking at the discrete discrete part of this generation, and then we're updating. Basically, the only thing that is going to change from one step to the next is this reward function. So we are doing we have been looking into this kind of approximation as well in an earlier version of this work.
Brilliant. And in that setting, then the reward function just becomes the free energy or the elbow for each G.
Exactly.
Basically.
Exactly. So yeah, when I said like we didn't try, like I didn't think about like this variational based approach, because for me it was having everything together and then trying to optimize both the variational free energy and the parameters of the GFlowNet all together. But here the paper based on variational based is very close to the setting that we were discussing with Lance earlier, where we have, let's say, we're training the GFlowNet for a particular value of the reward function, which is now the variational free energy, and then we're using the GFlowNet to sample graphs to update our variational free energy, and then we're doing this kind of sequential setting.
Good. That pleases me enormously. Thank you very much.
Thank you so much, Tristan and Carl. Can everybody unmute their microphones and give Tristan another round of applause?
Thank you very much.
That was brilliant. Well, thank you very much again, Tristan, and hope to see you around some other time. And same.
Absolutely, yeah. Very, very much looking forward to meeting again.
Thank you. And thanks everybody for coming and for the nice discussion. Thank you, Carl. And see you soon.
See you soon. Thank you. Thank you both.
Thank you, everyone.